up to the last class, last discussion that we have, we discussed that in an inverted index, there are two major things that we want to store. One is the dictionary containing all the terms in the vocabulary or in the collection. That is, if there are m number of unique terms in the vocabulary, there will be m items in this dictionary, which is, you can consider a simple list. And the second part that we want to store is the postings or a linked list, formally called postings or posting lists, which is again a list for each of the term which are stored in the dictionary. The dictionary will be containing one pointer to the starting of the corresponding posting list of the corresponding term. Why we are doing this? Because during the retrieval, we will be given a query such as, say, a multi-term query such as Q1, Q2. I mean, we can, of course, not consider the comma, of course. Say there are three-term query, Q1, Q2, Q3. How the retrieval will be happening? As this dictionary is sorted in the lexicographical order or in the following the dictionary order, we will be able to perform a binary search using the individual query term in that dictionary, right? Because it is sorted. So binary search with each of the QI on dictionary, right? And as the dictionary is sorted in the dictionary order or lexicographical order, that's why this binary search is possible. Now, if we get, say, the posting list, in short I am referring to as PL of Q1, PL of Q2, and PL of Q3. If I apply an intersection between this posting list, we will be ending up with another posting list, which is posting list of, say, the entire query Q. If I say the entire query is represented by a capital Q, so posting list of capital Q will be basically the doc IDs, will be containing the doc IDs of those documents containing both or containing all QIs, right? So let's say the query is, say, Indian Premier League, or say IPL auction 2022. IPL auction 2022. So again, this will be the three terms, IPL auction and 2022. We will be getting the posting lists of IPL, that is all those doc IDs containing the term IPL, all those doc IDs containing the term auction, all those doc IDs containing the term 2022. Now, if we apply an intersection, we will be ending up with all those doc IDs containing IPL and auction and 2022, right? And if we apply an OR here or an union here, this will be basically all those documents containing the term either IPL or auction or 2022. So if I draw a Venn diagram, a simple one. So if this is the query term 1, if this is for the query term 2, and if this is for the query term 3, that is, the items in this Venn diagram, in these circles, are those doc IDs containing those doc IDs in which these corresponding query terms are present. Okay. Then Q1, or applying an AND, or basically applying an intersection, is basically considering this, only this part. That is all those documents containing all those three query terms. And union is basically all the terms here. Okay. Now, we also discussed about, so this is the basic need to apply or to construct the inverted index, so that during the retrieval we can quickly look up the corresponding posting list of a given query term. Now, the posting list should be compressed so that it can fit inside the memory, or so that we can save some memory consumption. Now, note that another thing that we have discussed so far is this thing should be always in the main memory or in the RAM, right? This should be in the main memory, or basically the RAM. Now, this pointer, so this, as compared to the dictionary, will be much more larger in size. Because as we can understand, a term can be occurring in multiple different documents, right? And if we consider each doc ID as an integer, we know the size of an integer is basically either 4 or 8 bytes, right? Now, if the document is present, if the term is present, say in n number of documents, then for this term the posting list will be 4n, will be taking basically 4n amount of memory to just store the doc IDs, if I consider 4 byte size for an integer. 1, let's consider this. So 1 is a small integer, but if we declare int I equals to 1, we know in the virtual memory space, this will be taking a 4 bytes memory space, right? 1 will be taking 4 bytes, as well as 174, that will also be taking 4 bytes or 8 bytes, depending on your processor and your compiler. But note that this posting list can actually reside in the secondary memory, that is our hard disk, right? And this pointer can actually be a pointer or an address into this hard disk or the secondary memory. But the bottom line is, this should be in the main memory and this should be in the hard disk or in the secondary memory. Now, in the last class, we have discussed how to compress this dictionary so that less amount of memory is consumed in the RAM, because we know that RAM is a very expensive, as compared to hard disk, RAM is expensive, and RAM is also very useful, because every program that we are running should be residing in the RAM. Now, we have compressed the dictionary. Now, posting lists are much larger than the dictionary, maybe more than 10 times larger than the posting list, than the dictionary. And note that there will be postings associated with each of the terms. So if there are m number of unique terms in the dictionary, there will be m number of posting lists or postings. And if each of this m is quite large, you can understand how much memory it will be taking up in the memory, in the hard disk. So we need certain mechanism to store this posting lists compactly. Now, one question that you might be having inside your mind is, we know that hard disks are pretty cheap, right? So the price of hard disk is quite much lesser than the price of RAM. Then why are we so much concentrating on reducing the space consumption in the hard disk? The reason is the seek time that I have discussed maybe couple of classes back. So the seek time is basically the amount of time to take certain information which is stored in the hard disk to bring inside the RAM. The time consumption to take certain information stored in the hard disk into random access memory or the primary memory. Now, if the amount of information that is stored here is quite large, then that large amount of data should be transferred, which will be causing an increment, causing a significantly large amount of seek time. Instead, so let's say we are transferring I amount of information from hard disk to RAM, right? Now, instead of storing I, if we are storing I prime, which is basically a compressed version of I, then the seek time can be reduced. That is less amount of memory. So let's say the I is of size 500 MB. By compression, let's say it has become 300 MB. Okay. Now earlier, to bring in this 500 MB information from the hard disk to RAM, we need to transfer, although in chunk, but altogether we need to transfer this 500 MB space from hard disk, basically 500 MB information from hard disk to RAM. But if we compress, we can actually reduce the seek time, because now we are only transferring 300 MB, which will be taking less time. Of course, we need to decompress it in the primary memory as well, but decompression time is actually less than the seek time. Okay, so again, the primary target of compressing the posting list is to store each posting values compactly, in a compact way. Okay. All right. So we know a posting value is basically a document ID. Now we have discussed earlier what is a doc ID. Doc ID are certain way of identifying a particular document. As we have said, in a collection C, there will be multiple documents. Now a system should discriminate one document from the other using some kind of an ID. We are referring to it as a doc ID. And as we have discussed, generally we use an integer, say from base as 0, to represent the individual documents, or to identify, or we use an integer doc identifier or document identifier to represent each of the document in the collection. Now, so basically a posting value here is essentially an integer, right? Which is basically the doc ID, indicating in which document this term is actually occurring. For this term, in which document it is actually occurring. So each of them are basically integers, right? Now, if we consider the RCV1 collection that we are discussing, it contains around 800,000 documents, right? So for a term which is occurring in all the documents. So for that, so let's say the term the is occurring in all the documents. So in that case, the posting list of the will be containing 800,000 integers, right? Isn't it? Now, each of these integers, we know the size of int. Size of int is either 4 bytes or 8 bytes. Let's consider it is 4 bytes, right? Now, 4 bytes means we know it is basically 32 bits. Now, to store the individual doc IDs, we are spending 32-bit information in the secondary memory, in the hard disk, right? Now, in case for a term such as the, which is present in all the documents, so we need to, the posting list of the size of the posting list will be basically 800,000 into 32 bits. And you can understand how long the posting list, the entire posting list will be, right? Now, so, but let's consider having a document. I mean, again, if we consider this RCP1 collection, so we know in the collection there are 800,000 documents. So we need to represent, say, from, if we consider the doc IDs from 1, 2, 3, 4 up to say 799, 999, and then 800,000. So basically, if I consider these as the doc IDs, so they are essentially some integers, right? These are the numbers that we will be storing in the posting list. Now, if we consider the bit consumption, that is how many bit this integer, this decimal value need to be, needed to be stored in the memory, is basically 1 bit, right? Or 1 can be actually 1, because we know the binary form of 1 is 1. The binary form of 2, I hope you know, is 1 0. The binary form of 3 is, I hope you know, 1 1. For an example, let's consider what will be the binary representation of 27. We need to divide it by 2. The quotient will be 13. The remainder will be 1. Again, division by 2. The remainder will be 1. The quotient will be 6. Division by 2. Remainder 0. 1, 1. Right? So 3 divided by 2, quotient 1, remainder 1. So the binary representation of 27 will be these bit values, basically these bit informations taken in the from the backward direction to the first, to the first occurrence or the first bit. So 27, the binary of 27 will be basically 1 1 0, 1 1 0, then again 1 1. So this is the binary representation of 27. Now we know if we store 27 as int, it needs 32-bit. Int 27 needs 32 bits of information or bits to be stored. Instead, it can actually be stored using 5 bits. isn't it? Another thing is, if we consider the highest number here, that is the highest doc ID, the binary of uh, 800,000 will be containing around, I think, 19 bit positions. So basically, if we convert this decimal value into its corresponding binary representation, we will be ending up with a 19-bit string. Okay. Now, so essentially, we need not more than 20 bits, right? Why 20 bits? This is basically the mathematics. I hope you will be able to understand this. Why the base of log is 2? Because we know in a bit means it can store either 0 or 1, right? So there are two options. So given a bit say B, how many information, different information this B can store? Basically two. One is 0 and another is 1. Now if we concatenate 2 bits BB, how many different information this can store? 4. This is considered as, say, 0 and 1. This is again considered as 0 and 1. So using 2 bits, we can represent 0, 0, 0, 1, 1, 0, and 1, 1, and so on. So using a 20-bit string, 20-bit binary string, we can actually represent something, more than this 800,000, right? So again, our goal here is to use lot less amount of memory than this 20 bits per doc ID as well. So again, taking a recap, the general way of storing this doc ID is basically to store the integers, right? The integer, store the doc IDs as integer as it is. This is the first approach. So approach 1 is using int. Approach 2 is basically int of the, basically the decimal. Approach 2 is basically their binary representation. For this, we are understanding that we are reducing the memory consumption a lot. But we need to achieve something better than this as well. Okay. So let's consider a simple posting list. Let's say we have the posting list of computer, which is containing the doc IDs. The computer is present in a document having doc ID 283, 154, then again 283, 159, then 283, 202, and so on. Now, the approach to reduce the memory consumption is, instead of storing the doc IDs itself, we can store the gap. That is the difference between these two, and so on. Basically, what will be the posting list in this case for computer? So the first will be this, because this is the first document in which the computer is occurring. First, in the sense the first encountered document. Now, the next document that we are encountering is having a doc ID which is 5 greater than the last encountered document in which computer has been observed. So instead of storing this, we will be storing 5. Now, again, instead of storing this, we will be storing 43. So the postings will be, so earlier we have seen, so here we have said that these are basically the posting, the actual doc IDs. But here in a compressed manner, the doc IDs can actually be a simple doc ID. This is a doc ID. And from second onwards, there will be basically the difference. Right? Now, what will be the gap? I mean, for a frequent term, the gaps will be much small, because the frequent term, a frequent term is occurring in multiple documents frequently. So the doc IDs will be pretty frequent. So their gaps will be much small. In comparison, the frequency, the gap for a rare term, which is occurring in less number of documents, will be quite large. But still, using this approach, we can encode the small gaps using fewer bits than 20 bits. Because we have said in the RCV1 collection, the highest doc ID was this. So the highest difference can be when the document is occurring in the doc ID 1 and then it is occurring in the last document, the first and last encountered document. In that case, the posting list will be storing 1, which is the doc ID, and the difference, which is basically 7999. 799999. Sorry. This is the gap or the diff. Right? So, and we know that this kind of a rare term will be very rare, which is occurring in only 2 documents and they are present at the extreme ends. Right? So using this kind of an approach, we can actually reduce the space consumption. So basically, for a computer, in the first occurrence, we will be storing this. From second occurrence onward, we will be storing the gap. So in case we are storing the actual doc IDs, we were actually storing the upper part. For the storing the gap, the compressed approach, we will be storing this, the lower part. This as the doc ID, then onwards it's a gap. Now there is one advantage of this approach as well, which is we can actually store a doc ID which is much larger than an integer as well. That is, let's say there are, say, 1 billion document. Okay, so in the 1 billion document, let's consider a very frequent one. Let's consider a very frequent term which is occurring in almost all the documents in the collection. So in that case, I mean, if we store the doc ID and if the term is also occurred in the 1 billionth document, so 1, 2, 3 up to the 1 billionth doc ID. So these are basically the doc IDs which is stored in case of an uncompressed doc ID, uncompressed posting lists. So if the document, if the term is occurring in 1th document as well as some other document together with the 1 billionth document, then this 1 billion, basically 1, then 9 zeros, this will be the doc ID, right? Now this is needed to be stored in the posting list. Now instead of that, now we know certain compiler might be having problem with storing this value as an integer, right? So if we store the gap instead, it will be much, I mean, actually less than 1 billion. In practical, it will be much less than 1 billion. So the additional flexibility that we'll be having by using this gap is we will be able to store much more number of doc IDs than storing the doc ID itself. Okay, so that's it on the discussion of compressing the the discussion on the compression of a posting list, I would request you to have a read on these two chapters in the two books. And so we have finished the discussion on how to get the term statistic, how to use them, and how to compress the posting list in order to how to compress the inverted index in order to save some memory.